I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on quantum physics, blackbody radiation, and the photoelectric effect. In this series of videos, we're going to be talking about modern physics, which is quantum physics, atomic physics, and nuclear physics. In this video, we're going to start with quantum physics, talking about blackbody radiation and the photoelectric effect. We're going to start with blackbody radiation. At any temperature, an object emits electromagnetic radiation. This is called thermal radiation. The spectrum depends on the temperature and properties of the object, and the spectrum can range from infrared to visible light to ultraviolet parts of the electromagnetic spectrum. Now, at low temperatures, the objects have long wavelengths of the electromagnetic spectrum, which is not visible, and the wavelengths are on the infrared side of the radiation, long wavelengths, which means short frequency. Now, as it's heated, it starts to glow red like a burner on your electric stove, and at higher temperatures, it glows white, such as the filament inside of a light bulb. Now, to calculate the power that's radiated by a black body, we're going to use the Stefan-Boltzmann law, which is this equation. And the capital P stands for the power emitted by the black body, measured in watts. A is the surface area of the object in meters squared. The lowercase sigma is the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. And T to the fourth, capital T, represents the absolute temperature of the Kelvin scale. So that value is measured in Kelvin. Now, what a black body is an ideal physical object that absorbs all electromagnetic radiation. So imagine the surface like a bunch of little caverns that has a tiny little entrance, and light enters into that and reflects around in that cavern. And as it hits the surface, remember two things happen: some reflects and some absorbs. And that light continues to reflect until all of the electromagnetic radiation is absorbed into the black body. Now, Wien's displacement law is the wavelength at the maximum or the peak of the graph times the temperature in Kelvin gives us a constant. So Y max is the wavelength at the curve's peak, and we're going to look at a curve here in just a minute to understand what that means. Capital T is the absolute temperature of the object emitting radiation in Kelvin, and that equals a constant of 2.9 times 10 to the negative third meter Kelvin, which is known as Wien's constant. Now, this can be used to calculate the surface temperature of a star. So the peak wavelength of light from our sun is 500 nanometers, and we want to know what is the temperature of the surface of the sun. So we can rearrange Wien's displacement law and get that T is equal to 2.9 times 10 to the negative third divided by the maximum wavelength, and that's going to equal our 2.9 times 10 to the negative third divided by the wavelength of 5 times 10 to the negative seventh gives us a temperature of 5800 Kelvin is the surface temperature of our sun. Now, the classical view, as objects are heated, the charged particles of the object are accelerated. And what happens, this causes the particles to emit frequencies of the electromagnetic spectrum. The classical model shows that as wavelength decreases, the intensity should increase. This means that as wavelength approaches zero, the intensity would approach infinity. The problem is the classic model fails, and it's not what was observed. So if we look at the observed graph, we can see this black line represents the classical theory, and Max Planck hypothesized that blackbody radiation was produced by small charged resonators. Now you can see the curves of 5,000 Kelvin, 4,000 Kelvin, and 3,000 Kelvin with the blue, green, and red respectively. And those curves represent the max wavelength that's perceived from a black body. Now the resonators only had certain discrete energies, En, which is given by the equation of E to sub n equals lowercase n times h times f. And this fit the curve perfectly. So E to the n is the energy of the black body resonators measured in joules. N is just a positive integer called the quantum number. H, which is the value that kept coming up for Planck, is known as Planck's constant, just 6.63 times 10 to the negative 34th joule seconds. And F is the frequency of vibration of the blackbody resonators, and that's measured in hertz. Now, in the late 19th century, it was discovered that light that was incident on a certain metallic surfaces emitted electrons from that metal surface. And this is known as the photoelectric effect. Now, the way the photoelectric effect works is inside a vacuum tube, you have two metal plates, one of those being the metallic surface that's going to emit those electrons, which is the E label, and then you have a collector plate. Then both of those plates are connected to a variable voltage source, and we set an ammeter that's hooked up to the circuit outside of the vacuum tube so that we can measure currents from the light emitting those electrons. When there's no light on the emitter plate, the current's going to read 0. Now, as we shine light on the emitter plate, the metallic surface then emits electrons that go to the collector plate. And then what happens is a current is produced even though the variable voltage is not having any value. So we have a 0 voltage. We're measuring a current through the ammeter that goes through the variable voltage source. Now, the light that emits the electrons from the emitter plate are called the photoelectrons. So that's what the name of the electrons are that go from the emitter plate to the collector plate, because light is what is emitting those electrons. Now, the direction of the potential, if we switch the direction of the potential and we make it negative so that the current is reading 0. So we vary that voltage with light shining on the collector plate until the value of the voltage is decreased to 0. And the value of this potential difference is called the stopping voltage because it stops the electrons from getting to the collector plate. So when we turn the voltage source on, we have a negative collector plate and a positive emitter plate. So what happens then is those electrons then come off of the emitter plate. Some of them get all the way to the plate, but not quite to collect to cause a current. And then others we can see that just keep getting about halfway or a quarter of the way, 3/4 of the way, and nothing actually gets through to the collector plate. So what this tells us is the maximum amount of energy that the electrons have based on the stopping voltage. Now, the stopping voltage, which is delta V sub S measured in volts, is the amount of electric potential required to stop a photoelectron. Now, if the stopping voltage is 1 volt, then the photoelectron is said to have 1 electron volt of energy. So that 1 electron volt of energy is equal to 1.6 times 10 to the negative 19th joules of energy. Now, the stopping voltage, if we look at that with light intensity, so we know that if we graph current versus voltage, we know the stopping voltage is going to be a negative value. So we're going to have a current that increases up until the point of where the voltage is 0, and then it becomes relatively constant. Now, if we label our stopping voltage on the negative side, and if we increase the intensity of light, so a capital I1 represents the first intensity. Now, if we increase that intensity, what happens is the intensity increases the current, but it does not change the stopping voltage. So the stopping voltage remains the same, even though the intensity of light increased from I1 to I2 to I3. So the stopping voltage is unaffected by the intensity of light. But what it does change is the number of photoelectrons. That increases, which is why the current increases, because we have more charge passing through given points at a time because there are more electrons that are going from the emitter plate to the collector plate. That's what increases the current. But the energy of those photoelectrons is not any greater based on the intensity. Now, if we look at a graph of current versus voltage when the frequency is changing, we're going to have the same shape graph for the stopping voltage being negative. So we have red being a lower frequency. So the frequency as the current's going to end up at a constant. Now, if we increase the frequency, you can see that the stopping voltage shifts to the left, meaning it's more negative. And if we increase it again, it shifts further to the left, making a larger negative value. And remember, the stopping voltage is the amount of energy that the photoelectrons have. So The stopping voltage being greater at higher frequencies means that if the light has a larger frequency, that means the photoelectrons are going to have a larger value of energy going from the emitter plate to the collector plate. So the frequency is what the photoelectron's energy is dependent upon. The larger the frequency, the larger the photoelectron's energy value is. Now the stopping potential is more negative, as we said, at higher frequencies. Higher frequency of light transfers more energy to those photoelectrons, causing those photoelectrons to have a larger kinetic energy, meaning that they're going to move quicker across the gap between the plates. Now, if we use the stopping voltage and the frequency of light, a graph of electric energy versus frequency can be produced. And that graph was a direct relationship that stops at the horizontal axis at some value. Now, if we look at the graph properties, so the x-intercept, this is known as the cutoff frequency. So any value of frequency below this cutoff frequency is not going to produce photoelectrons because it just does not have enough energy transfer to those electrons to cause them to break free from the binding energy of those atoms that the electrons are attached to. Now, if we look at the slope value, the slope rise over run, the change in energy over frequency, that's equal to Planck's constant, 4.14 times 10 to the negative 15th electron volt seconds. And this actually is the equation that Max Planck found with the blackbody radiation, is that energy is equal to Planck's constant times frequency. And this photoelectric effect experiment is what showed and proved Max Planck's blackbody radiation equation works. So if we extrapolate that graph to the vertical axis, the y-intercept has a meaning as well. The y-intercept represents something called the work function, or the binding energy of the electron in electron volts. So the work function is the amount of energy that's required to make a photoelectron from an element. So if we have a metallic plate, the work function is how much energy is needed to eject the electrons with zero kinetic energy. And if we have more than that, then that causes the photoelectrons to move across the gap. So since we have a line, what we can do is we can write an equation in y equals mx plus b form. So Kmax is our y value, and that's going to equal our slope, which we know that the slope delta Kmax over delta F is just Planck's constant. And then we multiply by the frequency. And then our y-intercept, our work function, is the Greek letter phi. And since it's a negative value, what we're going to do in our equation is we're going to subtract that value. So it's going to be minus the work function, or the Greek letter phi. So looking at each of those values, Kmax is the maximum amount of kinetic energy an electron receives by absorbing a photon in electron volts or joules. We'll talk about what happens when it doesn't reach the maximum amount of kinetic energy in the next video. And then our lowercase h we know is Planck's constant, and there's the two values of Planck's constant in electron volt seconds or joule seconds. F, that's just the frequency of light in hertz or inverse seconds. And the Greek letter phi is the work function or binding energy, or the amount of energy required to produce a photoelectron in either electron volts or joules. Since we're talking about energy, we can represent the photoelectric effect with an energy bar chart. We can define the system as an electron and a photon, and the photon is known as the quantum of light, which is the smallest amount of something. So this is the smallest amount of light is a singular photon. Now, the electron has that binding energy, which is the amount of energy required to eject it from its molecule in order to create a photoelectron. So the binding energy is a negative value. And then the photon comes in and has an amount of light energy that is the Planck's constant times frequency. That's how you calculate the energy of light, is E equals h times F. Now the photon then collides with the electron, and the electron absorbs the photon. So we have an energy transfer from the photon to the electron, which means that now the sum of the work energy and the energy of the photon is going to be the total kinetic energy of the electron, which is going to be the sum of those two. So just looking at the heights qualitatively, we have 4 plus negative 2, which gives us a height of 2. So not all of the photon's energy goes into giving it kinetic energy, it has to break it free of that binding energy first, and then the rest is what is the kinetic energy. Now we can write our energy conservation equation just simply by writing HF minus the value of our work function, and that's going to equal the value of the kinetic energy, the max kinetic energy of our electron. And we end up with our equation that we wrote from our graph. So Kmax equals HF minus the binding energy, the Greek letter phi. Now, the last thing we need to talk about is how to calculate the cutoff frequency, which is the horizontal intercept. So the horizontal intercept, to calculate a horizontal intercept, we know that on the horizontal intercept, the cutoff frequency, well, there is no energy. So we can set kinetic energy equal to 0, and we know 0 equals the light's energy minus the work function, so that's going to give us the light's energy is equal to the binding energy. And this is how we can calculate the value of the cutoff frequency. So this is the introduction to quantum physics, blackbody radiation, and the photoelectric effect. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @CaviCoaches.